In this lesson, we're going to be talking about the quotient rule. The quotient rule is a rule in calculus that allows us to differentiate functions where there are quotients inside of them. To be clear about what a quotient is, it's just when you have a function divided by another function. Just to help you actually visualize what a quotient looks like, let me go ahead and actually draw the function machine for it. Now, it is actually possible to differentiate this using first principles, but that's actually not such a good idea. Instead, we should actually use the fact that we already know how to differentiate products and functions inside of other functions. Because after all, we can always rewrite a quotient in the following form. I've just come up with a random number here, like 5 on 3, which is clearly a quotient of 5 and 3. It's always possible to bring the 5 out in front of the 3 and rewrite it like this. So these arrows over here just indicate that 5 on 3 is the same thing as 5 times 1 on 3. And now this 1 on 3 over here can also be rewritten as the reciprocal of 3. So it's just 3 to the power of minus 1. And now from this we can see that 5 on 3 is the exact same thing as 5 times the reciprocal of 3. Now the first thing is, does it actually matter that I used 5 and 3? Well, no. I could have used any numbers and this would always be true no matter what. So keeping this in mind, we're going to go ahead and convert this quotient into this form over here as well. So now that we've actually replaced this for this, it's actually going to be possible to compute this using rules that we've already derived. Now the first thing to notice is that we can calculate this quotient using this machine, but this product over here does not actually get computed by the same machine. So what I'm going to go ahead and do first is I'm going to draw the machine that computes this. So it's pretty interesting to see that the machine on the top and the machine on the bottom perform different actions, but somehow for the same value of x, they always come up with the exact same value for h of x. Therefore, we'd say that this function is completely equivalent to this function. And therefore, if we can find the derivative to the bottom function, then we'd also get the derivative to the top function for free. So notice that in the top function, we take x and feed it through f and g, and then we take those results and divide them to get the value of h of x. But on the bottom function, we take x, feed it through f and g, but then we take the reciprocal of g, and then we multiply the two results, and we still get the exact same number, h of x. So we don't know how to differentiate the function in this form, but in this form we can easily differentiate it if we know how to use the chain rule and product rule. Now that we've actually applied the derivative to both sides, we just like to simplify the right-hand side into something that's easier to use. The first step is going to be to apply the product rule, because we actually have two functions being multiplied on the output over here. Now it looks like things got a little bit more complicated, but bear with me for a minute because they're about to get way simpler. First off, I'll rewrite this as f-x, and then I'll rewrite this reciprocal by putting it on the bottom. And now we can actually multiply this f-x by 1 to put it on the numerator. Okay, so now that we've dealt with the first term, let's look at this term over here. As you can see, there's actually a function inside of another function. So we're going to go ahead and use the chain rule by covering this up and differentiating the outer function first. So don't forget, when you use the chain rule, you actually have to put the derivative on the outside, as I did here. Okay, so the next thing I want to do is I want to get this minus 1 out of there. So I'll swap this plus for a minus, and then I don't really need these brackets anymore. And now the next step I'm going to take is I'm going to look at this g of x to the power of minus 2, and I'm going to rewrite it as a reciprocal. So I'm going to write it as 1 on g of x squared. Okay, so it looks like things are starting to finally clean up. So the next thing I'm going to do is I'm going to multiply this f of x and this g dash x by this 1 over here to put them on the numerator. Okay, so the last thing we're going to have to do is to write this whole thing as a single fraction. And to do that, we're going to need to rewrite this g of x as a g of x squared. Now, as you can see, this squared can just cross out with this g of x and we'd be back to where we started. But of course, now that both of them actually have a denominator of g of x squared, we can combine them into a single fraction. And now this equation over here is actually what we call the quotient rule. It basically tells us that in order to differentiate a function like this one, where you have f on the top and g on the bottom, it tells you that you first differentiate the top and then you leave the bottom, and then you subtract off the top minus the derivative of the bottom, and then after all of that you square the bottom and put it on the denominator. Now this is actually awesome because this is the first rule of calculus that you got without even having to look at the first principles definition. Now before I conclude, I should also show you how to use this formula. So let me go ahead and bring up an example and we'll work through it together. Okay, so as you can see here, we'd like to find the derivative of this function over here, 3x squared minus 4 on x plus 2x cubed. In order to do this, we should recognize that this top function over here is just f, and the bottom function over here is just g. And now, I'll just go ahead and differentiate both of these functions as well. Okay, so we can see that the derivative of 3x squared minus 4 is just 6x, and the derivative of x plus 2x cubed is just the same thing as 1 plus 6x squared. And now the last step is to just take this quotient rule and replace all of the functions over here. Okay, so now this thing over here is actually the derivative of this function over here. Now, one of the things you might notice when using the quotient rule is that functions like this one over here tend to get a lot more complicated. And this is actually something that basically always happens. This happens because in the original function, you've only really got 2 terms that you have to worry about. But then when you use the quotient rule, you've actually got 5 terms over here. And because of this, whenever you get a function like this and you go ahead and use the quotient rule on it, you probably want to expand and simplify the numerator and try to simplify this whole thing as much as you can. However, for our purposes, that isn't actually so important because I just want to show you how to perform the derivative calculation. Now, just like I showed for the superposition, product, and chain rule, I also have my own notation for the quotient rule as well. Now, in my notation, I represent different functions as different shapes, so all 3 of these represent different functions. And then I represent this function's derivative with this Checky version of the exact same shape. Now this is telling us that if we have some function that's given by some function divided by another function, then its derivative is given as the derivative of the first function times the second function, minus the first function times the derivative of the second function divided by the second function squared. It's really the exact same thing as this formula over here, just written a little bit differently. So I might as well give you another example, but I'll show you how I'd do it this time. Okay, so this time I want to differentiate x minus 5x squared on 3x squared minus 4x cubed. Usually I'd start by putting shapes around every function that I know how to differentiate. And then after this I just write out the box version of the quotient rule. Now this function on the left over here is just going to be h-x because it's the derivative of h of x. And then after this I just go ahead and copy over the functions that haven't changed. And now for the final step, I just go ahead and take the functions in the shapes and differentiate them and put them over here. Okay, so what we found is the derivative of this expression over here is just this giant expression over here. Now, if you wanted to, you could then go ahead and expand both of these terms and then simplify everything. But remember to be really careful when you get to this negative sign over here. I can't tell you how many times I've seen people make a mistake because of this minus sign right here. And now, just like it did for the last case, the quotient rule seems to have made things a lot more complicated. And this is something I think you'll just get used to. So whenever you use the quotient rule, be prepared to expand and simplify. And now with that, we've actually completed our examples. So now I'd just like to summarize this lesson. In this lesson, we investigated quotients in this form over here, and we decided that we wanted to differentiate them. Now, in order to do this, we didn't actually go back to first principles, but instead we wrote it in terms of a multiplication and a reciprocal. By doing this, we avoided going back to first principles, and we just used the quotient rule and product rule, which we already knew, to get this. By doing this, we were able to avoid using first principles. Instead, we got this expression which we could differentiate with the product rule and chain rule. After simplifying this expression as much as we could, we eventually ended up with this final form for the quotient rule, which is the way you'd see it in most textbooks. It's also possible, depending on the textbook you read, that instead of using F and G, they may have used U and V. But it doesn't really matter what letters we used, the main thing is the idea that we get across. And then finally, I introduce you to the box notation, which actually shows us the exact same thing, but in a slightly different way, which I personally believe actually makes the computation a fair bit easier. Now, if you don't actually want to use the box method, you don't have to. Either of these formulas actually convey the same information, and no matter which one you use, you'll always get the same answer, as long as you do everything correctly. And now with that, we've actually completed our discussion on the quotient rule.